In our follow-up on different type of machine learning problems, you would have realized now that classification and regression and clustering are not the only type of machine learning problems. There are other types of machine learning problems. There is one class classification, there is ranking, there is recommendation system design, but even that is not an exhaustive list. There are other types of machine learning problems as well. So for example, I'm just going to give these names so that you know about these, but if you follow the representation, evaluation, and optimization approach, you should be able to understand solutions to these problems. What's really important is to understand the problem in the first place before you start developing a solution for it. So there's a problem called ordinal regression problem, and I welcome you to explore what that is. It's a different type of regression problem. There's robust regression problem, like in which you expect that there are going to be a large number of outliers in your training data set. There's a survival prediction problem. So how long before this machine is going to fail because of a mechanical failure? Or how long is this person going to survive given that now that they have cancer? And we can learn from patterns of other patients to generate such predictions. There's also for image classification, for image tasks, you can have segmentation in which we are interested in identifying where does a particular object lie or what pixels in a given image belong to a certain object. You can have object detection tasks. So you're given an image, where is the face of a person? And we can localize that, and we can do also counting how many objects of a certain type there are in a given image. You can also have problems of generating imaging or data. Look at deep fakes out there, right? If you want to learn. There are also different types of clustering problems. So for example, there's a clustering problem called bi-clustering, in which you want to do clustering both with respect to the features and the instances. There is also a more general problem in which we want to design machine learning methods using machine learning methods. Okay, so that's called learning to learn. There are methods out there that use machine learning to learn to optimize. So rather than having a fixed optimizer, you can have an optimizer learn using machine learning. You can have feature selection problems in which your goal is to select the minimum set of features that are useful for a given classification problem. We've already talked about ranking. There are a bunch of others, okay? And I don't think any machine learning or any data science method can cover all of that. What I'm trying to teach you here is that look out for different types of problems and try to frame them as machine learning problems. You should have that capability yourself. Solving those is of course important, but for that there are libraries. The real question is, how do we formalize a machine learning problem as an optimization problem? Because then it's really easy for me to solve that, right? So that's the goal here. There are other types of machine learning problems. I'm just going to give you a very high level overview of what these problems actually are. So one of the machine learning problems that is quite interesting is called semi-supervised classification. So remember, we talked about supervised classification in which we want to separate apples and oranges, right? So you got a bunch of labeled training examples that are apples, and then you have these negative ones which are oranges, and you want to learn a discriminant that you have over here to separate these out. But getting labels is problematic. Actually, if you think of data science, one of the biggest problems in data science is actually getting labeled examples. That can be very, very expensive. So in the field that I work in bioinformatics, designing an experiment that tells you a given protein has a certain function requires a large amount of, typically a large amount of money and effort to get that particular label. Similarly, getting labels for medical data for, let's say, a biopsy of a certain person is really hard to get labels from pathologists because they can take a long time to get to a sufficiently large set. So is it possible that we used unlabeled examples in training? And that is the core of what this semi-supervised classification or learning does. So together with a bunch of training examples which are labeled, let's say we have got a data set of unlabeled examples for which we do not know the labels. Now, if we were to use only the labeled examples, we would get a classification boundary indicated by this line over here. But if you look at these examples which are unlabeled, we don't know their labels, let's say shown over here, we haven't labeled them yet. If we use this data and a principle, let's say that we should get a maximum margin line or a line that passes through low data density region, we can get probably a different classifiers which has the same generalization ability over the training exam, or the same prediction accuracy over the training examples, the label training examples, but it is probably going to generalize better. So that's the fundamental idea behind semi-supervised classification. It's a really interesting direction of research as well, and gives you really useful classifiers. Following up on that, most of the machine learning models that we have dealt with are called inductive models. That is what we are doing over here is inductive learning. And what that means is I give you a bunch of training data that is labeled. We have got xi with the corresponding yi for all I is equal to 1 to, let's say, n examples. And then you give me a function you learn a function that has a certain set of hyperparameters, let's say the weights and the biases for that particular problem that are learned using this training data set. And then I use that function, or once I have induced that function, I use that function to classify different types of examples, right? So that's what we are doing. There's another type of machine learning problem called transductive learning. So we should call it transductive learning, not transductive SVMs. What these do, they're closely related to what we talked about in terms of semi-supervised classification. You've got a bunch of training examples which are labeled, but you have got a bunch of unlabeled examples as well, for which you don't know the labels. And what we want in transductive learning is use labeled data in conjunction with unlabeled data to specifically label the unlabeled examples only. So our objective is not to induce a function, but rather to generate label assignments for this dataset. So this is slightly different from what we talked earlier in semi-supervised classification, where we were using this data to induce a function still that allows us to classify these examples or other examples in general. But here the goal is simply to generate labels for unlabeled examples with the given training data set, and that's it. So it's sort of like a throwaway classifier that you're making. Okay. The next type of machine learning problem is called multitask problem learning. So you can have, let's say you want to predict the grade of an apple, and you can also classify what type of apple that is. So let's say this is an Arkansas black apple and this is a Yataka apple. You want to classify what that apple is, but you also want to give it a quality score. So what you have in your machine learning model, you feed it an image of an apple. So you give it an image as input, and what you want is two things. You want the type of the apple to be predicted, and you also want the quality of the apple to be predicted. So you can essentially, you're learning two tasks. And if these two tasks are correlated, or if one task informs on the other task, you can essentially get better or more improved prediction accuracy. So this is what lies in multitask learning. There's another problem called transfer learning, in which you train a machine learning model to learn to solve one task, let's say apple versus oranges, okay? And you use this machine learning model or the features that are extracted for this machine learning model to solve another related task, let's say pear versus mango classification. Okay, so use information from one task to classify another is called transfer learning, and this is typically used in deep neural network models that we're going to talk about soon. You can also have multi-label classification, right? Let's say if you got a machine learning problem in which you were given a picture as input, and you want to design that machine learning model to identify different types of fruits in that picture. Now, if that picture only has one type of fruit in it, you will essentially classify that as, let's say, if the input is an apple, you have an apple output, you can have a mango output, you can have, let's say, oranges, pears, all types of fruits, right? Pineapples. Okay. So typically what we do is single label classification. That is, we take a single instance as input and we determine what its corresponding label is, right? Whether it's an apple or an orange, right? But what if we want to do this, that we've got an image as input that contains multiple images, multiple fruits, and we want the machine learning model to be able to predict what fruits are in there. So let's say there are apples in there, there are mangoes in there, and there are oranges. So you're generating a multi-label output. So does a picture have apples, oranges, or mangoes? Those type of questions can be answered using multi-label learning. Remember, all of these learning problems that we've talked, multi-label learning or constructive learning, they have their own definitions of loss functions and their own representations. You can also have structured output prediction problems. So let's say if you want to classify a given image into, you want to identify what disease a particular person has. So you give certain data for that disease as input, and you want to classify whether that person has that disease or not. But if that person has that disease, you also want to classify what type of disease that person has. So this is a sort of a hierarchy of learning problems. So you can have, first of all, whether it is a diagnostic. So whether this is positive, negative first. And if it is positive, if it's negative, we don't care because that's normal, right? So we don't care. But if it is positive, what type of classification, what type of problem is it? We can have, let's say, a certain type of abnormality like left bundle branch block for a heart patient or a right bundle branch block and so on. So you can learn all of these or these two things simultaneously by using structured output learning. Remember, if there is a structure in the output of your machine learning labels, then you can use structured output learning. So let's say you have, for a given instance, you have a label that you want to generate that looks like this. And because there can be relationship between the various variables that you want to predict, this is what is going to be structured output learning. So think of it like this. If a person's forearm is over here, then we know that if a person's part of the arm is over here, then that there is only a small amount of area where the next part of the arm is going to be. So a machine learning model can benefit from learning this type of structure that is inherent in the problem and to give you better output predictions. It's very commonly used in image segmentation and hierarchical learning tasks. Okay, and also used in structured output learning is also used in machine translation. It's also used in, let's say, we can have, for a given sequence, we can use audio to generate text, and then we can use the correlations between different parts of the text as a structure and to improve our prediction accuracy. There's another problem called active learning. So it's a special case of semi-supervised learning in which a learning algorithm is able to interactively query the user. So let's say if you want to classify the apples versus oranges and you have a very small training set, you can start making a very crude classifier and use that classifier to label unlabeled data with the help of an oracle or an expert for that field. So if you have an input, is the machine learning model essentially can ask a user, is this an orange? And if then it can get a label for that, and then it can update its internal representation or the parameters to improve its prediction. So this is a very interesting direction of machine learning or data science in which we can learn from oracles or from users while the system is being trained. Okay, so there's that. We can also do representation learning, in which our goal is to learn feature representations that can be useful for classification. So for example, what does an average cat look like? So this is the pattern that the Google brain has learned to classify cats with. So that's the goal of representation learning. There's also something called self-taught learning, in which our goal is to learn features automatically for a given classification problem without extracting features. So let's say I just give the raw image as input, and then it learns to classify using both labeled and unlabeled data to arrive at interesting features that can be useful. Another task is in machine learning is reinforcement learning. So let's say if you want to train yourself to drive and what essentially you want to do is, or if you want to develop a machine learning model that learns to drive, what you want is the machine learning model to be able to generate driving commands, whether I should steer left or steer right, or whether I should press gas or whether I should press a brake. And however, training for every possible case in using a supervised manner is going to require very detailed labeling and a lot of training data. So that is associated with, if there's a person right ahead of you, you need to steer clear of them, and there are going to be so many different types of rules. Fortunately, there is a method called reinforcement learning based on a reward principle. So just like if you reward a dog when you like their behavior, or you blow a whistle, an ultrasound whistle, if they don't do something you like, then the dog learns based on that to try to to behave in a certain way, right? We can reflect that in machine learning models, although it's not a part of this module itself. Reinforcement learning is one of the really cool techniques out there that has been able to generate some really interesting machine learning models. So let's say if you want to learn to fly a plane or play a tic-tac by yourself, by learning to play with yourself, this is how you can do this. So what you want is a machine learning model that maximizes its reward signals that it receives from a given environment to learn to modify its behavior. So if you want to watch a fun video on that, I've made one in which we train a machine learning model that is a rat brain or a mouse brain to steer away from a cat or escape from a cat. So there is a video on that. If you just are curious to explore this, you can watch that. And remember, this is not going to be a part of our module itself, this video in itself, but it's just something. If you're interested in exploring how reinforcement learning works, I think this would be a useful introduction for you. These reinforcement learning techniques have been used in solving protein structures. They have been used in solving different type of games. AlphaFold has certain aspects of it that are based on on uh, on on reinforcement learning to play Go. So all of those methods have a reinforcement learning principle built into them. So please go ahead and do that. There's also like survival prediction. We've already talked about that, whether we want to predict the survival of a certain patient. But the goal is just to sort of like a hidden intention was not to exactly intimidate you, but just tell you that there are different types of machine learning problems. However, don't be intimidated by these. All you need to do is build a representation of the solution. How can I solve this? That's the first bit. That is, how can I design a function that takes an input and does what we want to do? And then the second bit is the evaluation bit. Whenever that function or the representation that I have built doesn't do what I want it to do, how can I change the representation of that particular machine learning model through optimization for it to be able to do what I want it to do? Okay, so designing a loss function or doing an evaluation on that. And if you follow those principles, you can practically solve all of these problems and understand existing solutions using the same principles. Thank you.